Hello, mathophiles. In this adventure in algebra, we will discuss group properties. So now that we've defined what groups are and we've looked at several examples and proved that they are in fact groups, let's actually show what you can prove about groups in general. So these are statements about arbitrary groups. So here's our first fact. Let G be a group. So that means we have a multiplication that is associative with a multiplicative identity and inverses. Let little g be an element of capital G. Then G times G inverse is the identity, and G times the identity is G. Why do I point this out? Because if you've been following my videos, you will recall that my definition of a group has only been emphasizing multiplication identities on one side, because I pointed out it can be proven when you have an associative multiplication and these two identities that these other two facts automatically follow. And that's what I'm going to prove now. And so the disadvantage of that is you now get to have to sit through this proof. The advantage of that is that in your homework, you don't have to do these calculations for every single explicit example, and I haven't had to do these separate calculations in my other videos. I only have to do it once and for all. So first we start with multiplying on the right by the inverse. The sneaky trick, so yes, it turns out this proof is essentially a trick, is to magically insert the identity on the left. The motivation for why I'd want to do that is because it's quite clear if I had G inverse inverse times G inverse, I would actually get the identity. But I don't have that, I have G. So what I'm trying to prove is that G is equal to the inverse of the inverse. But it's actually hard to do that directly, and so we're going to be doing it in a sneaky way by bringing in the identity and then replacing the identity with this calculation, and then using associativity to actually get what we want. And that's exactly what we do. The next step is to replace the identity with this. G inverse times the inverse of the inverse. Now we can do this because this is a fact that we're assuming that for every element in the group, it has an inverse such that when you multiply it on the left by its inverse, you get the identity. And so in this case, we are applying that fact to H. And so we know this H inverse exists, and I'm calling it G inverse inverse. Yes, it turns out it's actually equal to G, but that's something we don't know yet. That's something we'll prove later in this video. The next step is associativity. If I treat G, this second product, as one element, so I have A, B, C in parentheses here, I can move the parentheses over. Now if I treat this product that I was treating as one element before as two elements, I now have these three elements and these parentheses. By associativity, I can move them over again. And why am I doing all this? Because I now have something that I can cancel, and so now I get what I wanted, this G double inverse times G inverse. That's exactly what I see. I now have G times G inverse on the left, which we know is the identity, because that's something we are assuming is true. And now the identity times G inverse on the left is just G inverse. And so now if we multiply on the left by E, we get G double inverse times G inverse, but they cancel again because you're multiplying G inverse on the left by its inverse, and we now get the identity, which is exactly what we wanted to show. It's a weird convoluted calculation, but it manages to show the result we have. And if you check carefully in this proof, you will see we definitely used associativity a bunch of times. And so if you're actually working with a set with a multiplication that is not associative, even if you had left inverses for every element and a left identity, this fact is not necessarily guaranteed to hold. This fact really relies on being able to have associativity. Now let's prove that right multiplication by the identity gives you the group element G back. This time the trick is to use the result we just had. So we now know that right multiplication by G inverse gives you that identity. And so now we could see that we could do cancellation if we do things in a clever way. In other words, I'm going to try to replace G times E with E times G, which we already know is equal to G by assumption that we have a group. And the clever way to do that is to replace E with G inverse G, which we already know we can do because we have a group. Moreover, because we have associativity, we can move the parentheses over. And because we just showed that multiplying on the right by an element on the right by its inverse gives you the identity, we know we can cancel here and get E. And so we do the calculation, and we now see that G times the identity is equal to the identity times G. But we're in a group, so multiplying on the left by the identity gives you the group element back. And so we get what we wanted to show. So very long proof, but the point of both calculations is that if you manage to prove that multiplying on the left by the inverse gives you the identity for every group element, and multiplying on the left by the identity gives you the group element back, then you get right division and right identity for free, provided that multiplication is associative. And so the upshot of this is that we can use these two properties and we never have to prove them for any specific group. And that is actually significant detail. I mean, I had actually gotten all the way through my PhD having to do this proof case by case for every specific example. All right, now that we finished talking about multiplication on the right by identities and inverses, let's talk about the cancellation property. So suppose we have a group. Suppose we have three elements in the group. If AB is equal to AC, then you can cancel out the A's and conclude that B is equal to C. Similarly, if BA is equal to CA, then you can cancel out the A's and B is equal to C. Note that we're not assuming commutativity. That's why these have to be separate statements, because they're not actually the same. In general, these are not always true for arbitrary sets with multiplication. So, before I do the proof, I should note that if you work with arbitrary matrices with multiplication, this property might not hold. If A is not an invertible matrix, you can actually get situations where this happens. In fact, this is already true for integers. I mean, it could be the case that if you take 0 times 1, that's equal to 0 times 2. But 1 is definitely not equal to 2. So this cancellation property is very, very special and relies on working with a group. So now we will give the proof. For time constraints, I'll only prove the first part. So we're going to assume that AB is equal to AC, and we want to conclude that B is equal to C. Now, a false proof might try to subtract from both sides. And, well, there will be a point in the course where we'll come back to this idea, because there is a time in the course when that's a reasonable thing to do. But right now that doesn't make sense, because what does it mean to subtract elements in a group? Well, for an arbitrary group, that doesn't make sense. So this idea is completely vague. We only have multiplication and inverses. So the only thing we can do to both sides of the equation is multiply both sides on the left by something. or multiply both sides on the right by something. And note, when you're assuming that multiplication is not commutative, order actually matters. So on the left or on the right, and you do pay attention. You cannot actually do something like putting a z in the middle. That's forbidden. So these are the only tricks we're allowed to do to equal signs at this point. So maybe we can multiply by some sort of cleverly chosen x on the left. Can you think of the right choice of x that would somehow get rid of the a? Well, the right choice would be A inverse. So since G is a group, there exists A inverse, such that A inverse times A is equal to E. Then multiplying the left by A inverse on both sides, you get A inverse times AB equals A inverse times AC. At this level of the course, as early on as we are, I will be careful about parentheses. So order of parentheses actually matters for right now. So these two quantities are the same. However, let's take a look at this left-hand side. By associativity, we can move the parentheses over. And A inverse times A is just equal to E, and E times B is just equal to B. And so we get this calculation. So the A inverse times A cancels. We get E times B. Since E is the identity, we get B back. So this expression on the left-hand side is actually equal to B. Worth noting, the role played by B here is such a way that if I just replace with C everywhere, I've actually just done the same calculation with the right-hand side. A inverse times AC is equal to C. Whenever you can do that, you can shortcut the calculation and just say similarly, A inverse times AC is equal to C. And hope that the grader is smart enough to see that all one has to do is replace one letter with another one, and it's the same calculation. If the only difference of the proof is replacing one letter with another, it's the same proof. And so what have we shown? We've shown B is equal to A inverse AB, which is equal to A inverse AC, which is equal to C. So B is equal to C, which is exactly what we want to show. So it's called the cancellation property because you're able to cancel the A's. And the reason why you're able to cancel the A's is because you're able to multiply on the left by A inverse.